The phase and frequency considerations of feedback amplifiers. To judge the stability of the feedback amplifiers with frequency, the two factors, the loop gain A beta and the phase difference between the input and output, are the two determining factors. Nyquist method is most commonly used to investigate the stability of the feedback amplifiers. The Nyquist plot is shown in the figure. The loop gain A beta is equal to 0 at the frequency. The loop gain A beta is equal to 0 at the frequency and phase angle are equal to 0. Frequency and phase angle is also equal to 0. As frequency increases from 0, f1, f2, f3, the phase angle also increases. As frequency increases from 0, f1, f2, f3, and the phase angle also increases. Here it is f1, f2, f3, it is f4, and here it is f5. Now the phase angle also increases. The loop gain A beta also increases. At the frequency f4, the loop gain A beta is equal to the length of the lane drawn from origin to point f4. The phase angle is equal to pi. At the frequency f5, the loop gain A beta is equal to 1 and phase angle pi is equal to minus 180 degree. As frequency increases, the A beta decreases back to 0. Nyquist theorem. The feedback amplifier is unstable if the Nyquist curve encloses the minus 1 point. It is the unstable. Is stable otherwise, that is, if it not is unstable if it is not encloses minus 1 point, and if it encloses and it is stable. So that the figure A shows the Nyquist curve does not enclose minus 1 point, so feedback amplifier is the minus 1 point is stable otherwise, that is, this one it is encloses the minus 1 point, so that it is unstable, and this one it is not encloses the minus 1 point and it is stable. So that in figure A, the Nyquist curve does not enclose minus 1 point, so feedback amplifier is stable. And in the figure B, the Nyquist curve encloses the minus 1 point, so feedback amplifier is unstable. Enclosing minus 1 point by Nyquist curve means the loop gain A beta is greater than 1. That is, the feedback signal is in phase with the input signal that results in the large input signal. The larger enough signal at the input results in the amplifier to oscillate. Gain margin, the negative value of A beta in decibels at the frequency at which phase angle is equal to 180 degree. Phase margin is equal to the 180 degree minus the phase angle at the frequency at which loop gain A beta is equal to 0 decibels. At the frequency at which loop gain A beta is equal to 0 decibels. Here the loop gain A beta, this one it is the loop gain, and here it is the frequency, so that this one it is the phase angle, so that the gain margin gain margin, this one it is the gain margin, and here it is the phase margin. So that the difference is that here the negative value of A beta in decibels at the frequency at which phase angle is equal to 180 degree. Negative value of the here the negative value of the gain in decibels at the frequency at which the phase equal to 180 degree. Here at this angle, the phase angle, it is 180 degree. So that here from here to here it is the negative value of the gain in decibels. Okay. Now the gain margin and the phase margin is equal to 180 degree minus the phase angle at the frequency at which loop gain is A beta is equal to 180 degree. Here the phase angle is the 180 degree minus the at the frequency at which the gain is equal to 0 decibels. Here at this point it is 0 decibels, and here it is 180 degree, and 180 degree minus this angle at which the gain it is equal to 0, it is the phase margin. The oscillator operation, basic block diagram of a oscillator is as shown in the figures. When switch is opened and a fixed voltage opened, a fixed voltage Vi is applied to the amplifier. The output voltage Vo at the fixed voltage Vi is applied to the amplifiers. The output voltage Vo at the amplifier stage output voltage is equal to A Vi. The feedback voltage is Vf is equal to beta Vo. Vf is equal to A beta into bracket of V. So that here amplifier feedback networks the input voltage, and here it is the output voltage. Here A is known as the loop gain by proper selection of the circuit elements of a amplifier and feedback networks. The loop gain A beta A is made equal to unity. Then the feedback voltage Vf, is equal to the input voltage Vi. Now the switch is closed and a fixed voltage at the input of amplifier. Now switch is closed and a fixed voltage at the input of amplifier is removed. The feedback voltage is large enough to drive the amplifier. The feedback voltage is large enough to drive the amplifiers and the feedback network that results in the amplifier to operate as an oscillator. The condition is that the loop gain beta A it is equal to unity. This condition is known as the Bergson condition for oscillations. So in practical feedback circuits, beta A is kept greater than unity. During the operation, beta A becomes equal to unity to generate the sustained oscillations at the outputs. The phase shift oscillators, here idealized phase shift oscillator is shown in the figure, and here it is the loop gain, and here it is a feedback networks, that is a amplifier, and here it is a feedback networks. So that the amplifier with high input impedance is shown in the figure is an inverting amplifier producing a phase shift of 180 degree at the outputs. The feedback network consists of 3 RC sections. To satisfy the Bergson's criterion, the loop gain A beta A is equal to 1. The total phase shift around the loop is 360 degree. The feedback network must have a 180 degree phase shift. By selecting the proper values of R and C, the phase angle can be adjusted to 60 degree. The total phase shift due to the RC sections is 180 degree. The Bergson criteria is satisfied. The circuit operates as an oscillator. The frequency of oscillation is F is equal to 1 upon 2 pi root 6 into RC. Here 1 greater than A upon beta, A greater than 1 upon beta, A greater than 29. The open loop gain of amplifier must be greater than the 20 nines. For the to operate as an oscillators, the open loop gain must be greater than the 29. The RC phase shift oscillator using the FET. Here FET oscillator circuit is as shown in the figure. Here RD and RS are the biasing resistances. Resistance RD and here it is the resistance RS are the biasing resistances. The resistance RD and RS are the biasing resistances. The capacitance CS is connected in parallel with the source. The capacitance CS is connected in parallel with the source resistance RS. A source resistance RS, a bypass source resistance RS as a bypass capacitance. The FET parameters are GM, that is transconductance, and RD, that is the drain resistance. The gain of FET amplifier is A is equal to GM RL. The load resistance RL, it is equal to capital RD. It is a small signal parameter, small RD plus small RD. The frequency of operation is F is equal to 1 upon 2 pi root 6 into RC. So that for the oscillations to occur, the gain of the FET amplifier, must be gain of the amplifier without feedback, it must be greater than the 29. Now the RC phase shift oscillator using the transistors. The transistor oscillator circuit is as shown in the figure. To avoid the loading effect at the input, the emitter follower stage followed by a common emitter stage is used for the high input impedance and the low output impedance. The voltage shunt feedback connection is most commonly used as shown in the figure. To avoid a loading effect due to the feedback network, the resistance R of feedback circuit is connected in series with the inputs. Here the resistance, the RDS of the feedback circuit is connected in series with the inputs, so that is connected in series with the input impedance of a transistor in series with the input impedance of the transistors. It is RDS, it is connected in series with the input impedance of the transistors. The frequency of oscillation is F is equal to 1 upon 2 pi RC square root of 2 pi RC square root of 6 plus 4 RC by R. That is the frequency of oscillations. The HFE of the transistor is HFE greater than 23 plus 29 R by RC plus 4 RC by R if the above condition is satisfied. If the above condition is satisfied, the circuit operates as an oscillators. The HFE of the transistor is specified by the manufacturers in the data sets. HFE of the transistor is specified by the manufacturers in the data sets. So that it is desired to design a phase shift oscillator using an FET having GM is equal to 5000 microseconds, while RD is equal to 40 kilo ohms and feedback circuit value of R is equal to 10 kilo ohms. Select the value of RC. Select the value of C for the oscillator operation at 1 kHz and RD for A greater than 29 to ensure oscillation action. Frequency of oscillation is F is equal to 1 upon 2 pi RC root 6 is equal to C is equal to 1 upon 2 pi R the root F into square root of 6. C is equal to 1 upon 2 pi into here it is R, it is the 10 kilo ohms and frequency it is 1 into 10 raised to 3 1 kilohertz and root 6 so that 6 is equal to C is equal to 6.49 the nanofarads. A is equal to GM RL. Assume the that is the A greater than 29. Assume A is equal to 40 to avoid a loading effect at the input of feedback, so that load resistance RL is equal to A upon GM upon 40 upon 5000 to 10 raised to minus 6. RL is equal to 8 kilo ohms. Because the A must be greater for oscillations to take place, A must be greater than the 20. So that here assume that the gain of the amplifier without feedback A is equal to 40. So that the to avoid the loading effect at the input of feedback, so that here the RL is equal to 8 kilo ohms. Now RL is equal to RD capital small RD plus small RD, that is the drain biasing resistance, and it is a FET parameters. So that from all these parameters the value of that the resistance RD, it is equal to the 10 kilo ohms. The RC phase shift oscillator using op-amp, the feedback network consisting of 3 RC sections provide a phase shift of 180 degree. The op-amp having a high input impedance and low output impedance eliminates the loading effect at the input and output of feedback networks. The op-amp is an inverting amplifier of 180 degree phase shift is produced by the op-amp. Is an inverting amplifier is produced by the op-amp. The op-amp is an inverting amplifier. 180 phase shift is produced by the op-amp, so that the loop gain beta is equal to 1. The total phase shift around the loop, it is equal to the 360 degree. So that the percussion criteria is satisfied. The circuit oscillates at the fixed frequency. Here this one, it is a fixed biasing circuit. This one, it is a inverting amplifier, so that the negative resistance, negative, positive. And now this one, it is an inverting amplifier producing 180 degree phase shift, and here it is the feedback network, it is producing a phase shift of 180 degree, so that the total phase shift, it is equal to 360 degree. Wien bridge oscillators. The Wien bridge oscillator is as shown in the figures. The resistance R1, R2 and capacitors C1, C2 are the frequency adjustment elements, so that the R1 is C1, here it is R2 C2, R3 R4. Resistances R3 and R4 for the oscillator operation. The resistors R3 and R4 for the oscillators operations, so that the output of the are the frequency adjustment elements. Resistance R3 and R4 are for the oscillator operations. The output of op-amp is connected to terminals A and C at the bridge. The terminals B and D of the bridge are connected to the input of the op-amp. The frequency of operation is F is equal to 1 upon 2 pi square root of C1 R2 C2. R3 upon R4 is equal to R1 upon R2 plus C2 upon C1. If R1 is equal to R2 is equal to R1, C1 is equal to C2 is equal to C, F is equal to 1 upon 2 pi RC. That is the R1 C1, here it R2 C2, R3 R4. So that from that one, the frequency of operation is equal to 1 upon 2 pi RC. Now R3 upon R4 is greater than 2, so that condition for oscillations, the value of resistance R3 must be greater than R3 2 times the 2R4. The percussion criteria for oscillation beta A is equal to 1 is satisfied. The circuit operates as an oscillators. Now calculate the resonant frequency of the Wien bridge oscillator as shown in the figures. Here this one, it is the resistance R1 C1 and resistance R2 and C2, so that here it is R3 and R4. So calculate the resonant frequency. The resonant frequency of oscillation is F is equal to 1 upon 2 pi RC is equal to 1 upon 2 pi here, because here R1 C1 is equal to R2 C2. Both are the equal values. So the 2 pi into 1 into 10 raised to 3 అంటే 001 into 10⁻⁻⁶ f is 3.1 kilohertz. Design the RC elements of a Wien bridge oscillator as shown in the figure for operation as at f naught is equal to 10 kHz. Resonant frequency of oscillations is f naught is equal to 1 upon 2 pi RC. Assume R is equal to 100 kiloohms and f naught is equal to 10 kilohertz. So that 1 upon 2 pi into 100 and 10 raised to 3 is C is equal to 0.16 picofarad. For the oscillations to occur in a Wien bridge oscillators, the resistance R3 must be greater than the 2 times R4. The resistance R3 must be greater than the 2 times R4, so that R3 is greater than 2 R4. Create the R3 by R4. That is, select R3 is equal to 3. Here, for the oscillations to occur in the Wien bridge oscillators, the resistances R3 must be greater than 2 times the R4. So that R3 greater than 2 R4, select R3 is equal to 300 kiloohms and R4 is equal to 100 kiloohms. The LC tuned oscillator circuits. The basic circuit of a tuned oscillator is as shown in the figure. A is an amplifier with a phase shift of 180 degree. X1, X2 and X3 are the LC elements. X1, X2 are the two inductances or the two capacitances depending upon the two types of the LC tuned oscillators. Depending upon that, two types of LC tuned oscillators are Hartley oscillators and Colpitts oscillators. X1, X2, X3. Here X1, X2 are the two inductances or the two capacitances. L1, L2 are the inductances. C1, C2 are the capacitances. The Hartley oscillator circuit. The Hartley oscillator using a common emitter transistor is as shown in the figure. The reactance of the is as shown in the figures. The Hartley oscillator using a transistor is as shown in the figures. Okay. And the Hartley oscillator using common emitter transistor is as shown in the figure. The reactance of RFC is higher, so that at high frequencies it is open circuited. At high frequencies the RFC coil is high, so that at high frequency it is open circuited. At high frequencies the reactance is 0. The reactance is 0. RFC coil at high frequency it is open circuit, because at high frequency its reactance is 0. In DC conditions, the RFC is used to isolate the AC and the DC. The reactance is 0 in DC conditions. The reactance high frequency it is open circuited, so that here the reactance of RFC is high at high frequencies. It is open circuit, so that at high frequencies the reactance is 0 in the DC conditions. Okay. RFC is used to isolate the AC and DC. The common emitter is having 180 degree phase shift at the output. 180 degree phase shift at the output. The common emitter is having 180 degree phase shift at the output. The L1 and L2 are the grounded, so that capacitor C is connected in parallel with the L1 and L2. That forms a tank circuit. The output of tank circuit is 180 degree phase shift. The Bergson criteria for oscillations is satisfied. The circuit operates as an oscillator, that is beta A is equal to unity. The frequency of oscillation is the x1 plus x2 plus x3 is equal to 0. So that x1, x2 are the inductances and x3 is the capacitance. So that x1 plus x2 plus x3 is equal to 0. x1 plus x3 j omega L1 j omega L2 minus 1 upon j omega c. So that but j square is equal to minus 1 j omega L plus j omega c2 is equal to j square upon j omega c. So that omega into bracket of L1 plus L2 is equal to j upon omega c. So that omega square is equal to 1 upon c. omega square is equal to 1 upon c into L1 plus L2. F is equal to 1 upon 2 pi c is equal to L equivalent. Equivalent inductance is L1 plus L2. So if mutual inductance is between L1 and L2 is also considered, then equivalent inductance L1 plus M is the mutual inductance. Now Colpitz's oscillators. Now the Colpitz's oscillators are to RFC, RE. The Colpitz's oscillator is as shown in the figures. Transistor is under common emitter configurations. The R1, R2 and RE are the base. The R1, R2 and RE are the basing resistances. Are the basing resistances. CC1 and CC2 are the coupling capacitances. Are the coupling capacitors at the input and the outputs. The RFC coil is used to isolate AC and DC. Here this RFC coil, radio frequency coil, is used to isolate the AC and DC. The feedback circuit is a LC tank circuits. Capacitors C1 and C2 are grounded with the inductance L. Capacitor C1 and C2 are grounded with an inductance L connected in parallel with the combination of the C1 and C2, so that the percussion criteria is satisfied, that beta is equal to unity, then oscillations occur. The frequency of oscillation is from the basic circuit of the oscillators. X1 plus X2 plus X3 is equal to 0. X1, X2 are the capacitors and X3 is the inductance, so that X1 plus X2 is equal to minus X3. 1 upon j omega c1 plus 1 upon j omega c1, it is equal to minus j omega L. So that 1 upon j omega 1 by c1 plus 1 by c2, it is equal to 1 upon omega into bracket of 1 by c1 plus 1 upon c2 is equal to minus j omega L. So that minus 1 upon j omega into bracket 1 by c1 plus 1 by c2 is equal to j omega L. J square is equal to